Hello everyone, my name is Arya Mazaheri and I would like to introduce a new method for accelerating Winograd convolutions. Deep learning is the art of creating machines that perform functions which require intelligence when performed by people. I think you all agree that deep neural networks are everywhere, from object detection, semantic segmentation to intelligent agents. Improving the efficiency of these applications largely promote the usage of AI in our daily life. Convolutional neural networks learn to transform input data such as images into successive layers of increasingly meaningful and complex representations. Convolution operations consume more than 90% of the whole computation, and to further accelerate deep neural networks, we need to optimize these layers. We have different types of convolution, such as direct convolution, GEM, fast Fourier transform, and last but not least, Winograd convolution. Previous studies showed that Winograd's algorithm can minimize the number of arithmetic operations for performing small convolutions and run 2 times faster than the direct method. Winograd is composed of 3 steps. Let's see how Winograd convolution works in practice then. In this example, we would like to apply a convolution to an input image. First, we select the tile. Then we transform both the input tile and kernel into another space using Winograd transformation matrices. These matrices are predefined and their size depend on the output tile size, denoted by M, and the filter size denoted by R. In the second step, we obtain the element-wise multiplication of transform input and filter, and in the last step, the output should be transformed back into the original space using Winograd output transformation matrices. To fully benefit from the convolution, we need to pick a suitable output tile size M, which meets the expected accuracy level and memory limitations. Furthermore, additional overhead exists due to 6 additional multiplication steps for Winograd transformations. Therefore, the question that we have answered in this paper are as following. Can we reduce the overhead of Winograd transformations? What's the proper way to choose the right internal tile size? Is it possible to run Winograd efficiently on a wide range of GPU platforms? Let's take a single Winograd transformation and see how we utilize symbolic computation to simplify the process and reduce the overall overhead. Rudimentary implementation of 2-dimensional Winograd transformation requires us to perform a matrix multiplication which takes 3 for loops to do the job. Imagine that we have 6 of these and they will impose a lot of overhead. However, since the transformation matrix elements are predefined, we can do prior analysis to simplify the multiplication. Thus, with the help of symbolic computation, we remove constants such as zeros and ones, represent the matrix by indices, apply factorization, and remove common subexpressions. The result matrix is much simpler, and the code after optimization only needs a single loop, which can be also unrolled if necessary. We can implement Winograd convolutions in 2 different ways, non-fused and fused. A fused implementation is often desired as it reduces the GPU memory transfer by merging all the Winograd steps into a single kernel. We define a template for each implementation and then let the code generation fields the placeholders and generate the code for any GPU platform using OpenCL, CUDA, or even Vulkan. It is generally hard, even with metaprogramming, to develop comprehensive yet efficient Winograd convolution that can run across various inputs and hardware platforms. Therefore, we employed an auto-tuner to pick the right value for various tuning knobs which exist in our kernel. Using these methods, we could reduce the Winograd transformation arithmetics by up to 60%. A very interesting observation is that when internal tile size of Winograd is equal to 8, we can optimize the code to a greater extent. Furthermore, our generated Winograd code is now performance portable and can even compete with vendor libraries on 3 different platforms, such as NVIDIA, AMD, and even Mali G71 mobile GPU. If you're interested in this research, please feel free to contact us. Thank you.